So sorry for the interruptions. Next, coming back to every vector in span S can be uniquely written as a linear combination of vectors of S. That is the set of all linear possible combinations, that is span S, and every element can be uniquely represented as a linear combinations of vectors of S. If, just a minute, okay, if S is a generating set for a subspace W, then no proper subset of S is a generating set of W. That is, span of S equals to W, then no proper subset can generate W. And this is okay. No proper subset can generate W. Then what does that imply? That implies the set S must be linearly independent. So if you have a set such that no proper subset of it can generate the subspace W, then you can say this is linearly independent. Now coming back to our main topic, that is basis. What does it mean? Define basis. What is that? A basis beta for a vector space V is a linearly independent subset that generates V. So, what is basis? Basis is no subspace. It's simply a non-empty subset of V such that span of beta equals to V and beta is linearly independent. Both the properties must hold. It's spanning the whole space and this is linearly independent. But from the earlier one we can say from here, a basis is always a maximal linearly independent set and minimal generating set. Always keep in mind, a basis is a maximal linearly independent set. That means no proper subset of that basis is linear, no superset of that basis is linearly independent, and this is the minimal generating set. No subset smaller than that can generate the vector space V. So maximal linearly independent and minimal generating set. There are some examples of basis like the finite empty set. Span of that empty set is 0 and phi is linearly independent, so phi is a basis for 0 vector space. And this is very common for interview purpose. Like, what is the means 0 is a vector space, trivial space. What is its basis? Its basis is the empty set. Good. Now, n-tuple vector space. You know, Fn over F is a vector space. Okay. What is that? What is the basis of Fn F? Can you imagine? Basis of Fn F. Fn means its elements are n-tuple. So, suppose n is 2, R2. In R2 I have told 1, 0, 0, 1 generates the space R2, and these two are also linearly independent. You can check using the definition C1 of U1 C2 plus C2 of U2 equals to 0 implies C1 and C2 both are zeros. Similarly, you can say this is the basis of Fnf, where EI's are 0, 1 at the ith position and 0 elsewhere. Total n elements. Okay? Like this, but basis is a finite set. So, its dimension is finite. If the basis contains finite number of elements, then the dimension of that vector space is finite. So what is dimension? Dimension is nothing but the number of elements in basis. But is it always true that dimension should be finite in all cases? No. For the vector space PF, its basis like this. It is infinite dimensional vector space. But F and F is finite dimensional vector space. Dimension of m cross n f equals to mn. So this is also finite dimensional vector space, like that. Okay. Now there are some properties of basis. What are those? Let us go through that. This is I have already mentioned. If some non-empty subset of V, that is S, such that span of S equals to V, then it is easy to get that basis, because that basis must be a S or beta must be S or some subset of S, because beta is the minimal generating set. Already you have a set that generates V, so some subset or maybe that one is the basis of V. If V is finite dimensional vector space, then no linearly independent subset contains more than dimension of V vectors. Okay. Another important thing is that a set may have, like suppose R2. You have one basis, okay, and this is called the fundamental basis of the vector space R2. You may have another basis, but the number of elements in the basis is always same. So dimension of a vector space is always the same, but the basis is may be different. Okay, you may have a different basis. It's not like that basis is always unique set. No, it may be different, but dimension always same. For every finite dimensional vector space V, you can always find two subspaces W1 and W2, such that V can be represented as a direct sum of W1 and W2. This is in case of finite dimensional, not in case of infinite dimensional. If UV is a basis, then there are some scalar multiplication or scalar multiplication set is also basis. Why? You can check C1 AU plus C2 AV equals to 0. This is linearly independent, because A not equals to 0, then C1U plus C2V equals to 0. That implies C1 equals to 0 equals to C2, because UV is a basis, so U and V are linearly independent. That makes C1, C2 both are 0. Pnxy, in case of Pnxy, dimension of Pnxy is n plus 1 into n plus 2 by 2 factorial. If it has 3 variables, then dimension is like this. Infinite dimensional vector space I have mentioned. Now W1 and W2 is the smallest subspace of V that contains both W1 and W2. What would be its dimension? Dimension of W1 plus W2 is dimension W1 plus dimension W2 minus dimension of W1 intersection W2. So you must think about dimension of W1 plus W2. I am writing out the result, but you must think about why it is so. Okay? Dimension of W1 intersection W2 is less equals to n. Why? Because span of the intersection of two sets is a proper subset of span of S1 intersection span of S2. That's why dimension of them must be less than equals to. And also this. If V equals to W1 plus circle W2 and beta 1 and beta 2 are two subspaces of the vector space W1 and W2, then beta 1 intersection beta 2 is phi and beta 1 union beta 2 is a basis of V. Okay? These are based on this quotient space. You must go through it. Another important result is let dimension of V equals to n. Cardinality of F. Cardinality you must read. That is not covered here. Cardinality you must read. And cardinality of the field is p to the power k. Then the number of bases V is given by this formula, and number of subspaces of dimension k of V is given by this formula. And at least one question you can think of from this formula will be coming in CSI unit. So read about or mind these formulas very carefully. That's it. Now let's go back to solve some problems. Let's coming back to the problem that I have just mentioned. Yeah, this one. V is your V, dimension of V equals to 3. Read the question first. V be a three-dimensional vector space over the field F3. So, cardinality of F 3 to the power 1. The number of distinct one-dimensional subspaces of V. If you go through the formula, you will find the number of one-dimensional subspaces equals to 3 to the power 3 minus 1 by 3 square, that is p to the power k minus p to the power k minus 1. This is equals to n, this is equals to p to the power k. So, three to the power 1 minus 1. 13 will be your answer. Questions are coming like this and you need to remember the formula. Another problem. Let Pnx equals to x to the power n. Okay. V equals to span of 1 x squared dot dot dot. So V is what? V is nothing but your P of R. Set of all polynomials is a vector space. You know PR is a vector space and this is also linearly independent set. So is a vector space. It's a subspace obviously because set of all continuous functions there are many. And also you remember the vector space, it's a subspace of itself, that is trivial subspace. So this answer is also correct. This is linearly independent as I have mentioned. trigonometric functions belongs to V. Why? Trigonometric functions means sin x, cos x. Think about their binomial expansion. Sin x is what? X plus, maybe I am wrong, you can check. But we can always write it as a linear combination. Like this. Of the elements of V. So, all the 4 options are correct. Another problem. Are you enjoying? I am enjoying. So, let's go through it. The dimension of the vector space of all symmetric matrices of order n cross n. Here you can remember a formula. Dimension of the set of all symmetric matrices of order n equals to half n plus 1. Why? Symmetric matrix means you have a diagonal element like this, and all the elements here are similar to the upper triangle. Now for first row you have n choices, for second row you have n minus 1 choices, because the A21 equals to your A12, like this you have 1 choices. So its dimension is nothing but, okay, that is half n into n plus 1. So whenever you have a vector space of all symmetric matrices, you know the dimension is this. There are given conditions A11 equals to 0 and trace 0. Since you have given 2 conditions here, so its dimension is simply, you can calculate half n plus 1 minus, you have given 2 conditions, one is this, another is this, so minus 2, and you will get an answer. You will get one of this answer, you can check. Okay, another one is also based on matrix. We have given 5 cross 5 matrices. A is either 0 or 1. This must be I. Row sum equals to 1 or column sum equals to 1. What is the number of elements? That is dimension of this. What are the possibilities? I can take simply identity matrix. Okay. Now, this is one choice. In first row, we have 5 choices. You can replace 1 in any other place and 0 in the other places. When you put 1, suppose here, then in second row, you have 4 choices. Because in that place, you can put 1 as your row sum and column sum are 1. Row sum means sum of the elements in each row is 1. Sum of the column sum means sum of the elements in each column must be 1. Similarly, you have in third row 3 choices. In fourth row, you have 2 choices and 1 choice. So, it's kind of permutation thing, and the number of elements in S must be 5 factorial. Okay? Because as you have this number of choices, so number of elements must be 5 into 4 into 3 into 2 into 1. That is equals to 5 factorial. This is the last question. Let V be a real vector space. So V is over the field R and x1, x2, x3 be a basis. So dimension of V, what? 3 Yes, 3, because we have 3 elements in the basis. Is it a basis? Yes. If you go through the slides, you will get that answer. Dimension of V is 3. Is this a basis? x1 minus x2, x2 minus x3, x1 minus x3. Let's check. Is it, if this is linearly independent, then as it has 3 elements and this is linearly independent, so we can say this is maximal linearly independent set, and these 3 elements generating the space V, so this will also generate as dimension is 3. Let's check about linearly independence, where Ci's are scalar. C1 x1, C1 plus C3 x1. In case of x2, C2 minus C1 x2 plus, in case of C3 x3, C2 plus C3 x3 equals to. Now x1, x2, x3 be a basis means x1, x2, x3 are linearly independent. That implies C1 plus C3 equals to 0, C2 minus C1 equals to 0, C2 plus C3 equals to 0. This implies C1 equals to C2. So if I use this one, this implies C1 plus C3 equals to 0. And also first condition, using 2 we get this. This is 1 and 3 are same. So we have infinite number of possibilities for C1 and C3. They may not be 0. So this is not a linearly independent set, and so it cannot be a basis. Okay. Thank you very much. Hope you are enjoying my lectures. If you really like it, please motivate me by liking and subscribing my channel so that I will upload more videos and you will enlarge and broaden your knowledge in basic mathematics. Thank you very much.